Welcome back. Today we will talk about section 1.1. Section 1.1 is all about functions. And in some sense, calculus is the study of functions. Functions are mathematical objects, very important mathematical objects, but you can find them in real life in many, many different places. For example, imagine a company that produces baseball bats. There's some cost associated with producing a baseball bat. And the company can probably construct a cost function that would allow them to say, if I produce 1,000 baseball bats, this is what it costs me. Or if I produce 1,000,000 baseball bats, this is the cost for my company. Another example of a function from everyday life maybe is a population function. You could imagine some sort of function that tells you the population of buffalo as a function of time, where time maybe is measured in years. We'll start with a definition of a function. We'll think about some ways that we can represent functions, and then we'll do a few more examples in this section. So to begin with, I'll just jot down the definition from the textbook. When I think about a function, I think about a rule or an assignment, and I think you'll see what I mean as we go through some of these examples. Again, this is in your textbook. A function is a rule that assigns to each input exactly one output. And so you might ask, well, what are the inputs and what are the outputs? And really they could be many, many different things. In calculus, in this class, inputs and outputs will typically be real numbers, but they don't have to be for the definition of a function. So for example, right, I might think about having just a set of some objects here, and these objects are object 1, object 2, object 3. And then I have a separate set of some objects over here. These objects happen to be letters, right? Maybe I have 4 objects over here. A, B, C, and D. And then I can define many different functions here, going from one set of objects to another set of objects. And again, there are many ways that we can represent this kind of function. For example, maybe 1 should go to A, maybe 2 should go to C, and then this object 3 can just be mapped over to D. And so these black arrows here on the board, I might think about those as being my function. And the name of the function is f. And so this picture represents a functional relationship between the objects 1, 2, and 3, and some of these letters in this other set. A different way to represent this same function could be to write some formulas. I could write f of 1 is equal to a. In other words, when I take 1 as my input, I plug it into my function, the output is A. Likewise, f of 2 is C, and f of 3 is equal to D. Now, I said the word, but I didn't write it. 1, 2, and 3 here, these are the inputs for this particular function. And then A, C, and D, really, are the possible outputs. B happens to be another letter in this set, but you can see, right, none of my inputs are going to B. So it's not an output for the function. You might have heard a couple of these other words associated with functions that I'll mention here in just a second. This set of inputs is called the domain of the function. Again, so the domain of f is the set of all possible inputs. The outputs, A, C, and D, these make up the range of the function. I mentioned a second ago that there are, in your book, 4 ways to represent functions. Your book gives a list of these ways. The way that you might remember from high school is the algebraic way, just giving a formula for the function. And so that's certainly one of the four ways. Algebraically. And so probably in high school or in pre-calculus or something, you might have saw something like f of x equals x squared, right? This is everybody's favorite function, the squaring function. So in this situation, I could imagine an input, right? Maybe my x value is 3. And then the function, the rule, this expression right here, really tells me what to do with this input. In other words, if I want to get an output, I should take x equal to 3, plug it into my formula wherever I have an x, and then this expression on the right-hand side of the equation really tells me what to do. This tells me what to do with that input. It tells me take 3 and square it. In other words, multiply 3 by itself. And so the output here is f of 3 equals 3 squared. Again, I just replaced the x with 3. And then I know what 3 squared means. That means 3 times 3. And of course, that's 9. Okay, so the output when the input is 3 is 9. Some other terminology associated with functions are names for two different kinds of variables. The letter x here, the input variable, is known as the independent variable. And then f of x itself, the entire expression f of x, is the dependent variable. So in other words, if y is equal to f of x, I'm just introducing another variable called y, then this variable y is a dependent variable. It depends on, its value depends on the value for x that I pick. Some other ways to represent functions are, right, algebraically was our first way to represent a function. A few other ways to represent functions are verbally. Right on the front board from a moment ago, I just said 1 goes to A, 2 goes to C, and 3 goes to D. And so I told you what that function was. I can represent a function numerically with a table of values, perhaps. In some of the examples in this section, you'll have a chance to work with functions that are defined by a table of values. And then lastly, they say visually as a fourth way to represent a function. When I hear visually, what I'm thinking of is somehow representing a function with a graph. I want to take a few minutes now and do a couple of examples that I think will help you with some of the exercises in this section. So maybe we'll start with example 2 in your book. So this is 1.1, number 2. I'm going to write the problem on the board and then we'll think about how to solve it. An internet retailer charges $4.99 for shipping. In other words, to ship an order that totals less than $25. And this same internet company charges $5.99 for and order up to $75. And then after $75, there's no shipping. And so they offer free shipping for an order over $75. And of course, I've lost my place here, bear with me. If G of P is the shipping cost for an order totaling P dollars, we're supposed to do a couple of things. We're supposed to state the domain and range of the function G. I'm actually going to do a few other things in this problem, but that's what the textbook says. The way that this particular function is defined is in a piecewise fashion. One of the topics in section 1.1 concerns piecewise defined functions, and we'll have an opportunity to work with these quite a bit as the semester moves along. What I mean by a piecewise function, I think you'll see in a moment, is that the values for G, right, the actual shipping cost, depends on what the order total is, how much the order total is. And so I can write a formula for G of P if I like. Here's what it'll be. G of P, it'll equal one of three different things, depending on, again, what the order total is. And so if the order total, right, if the price or the amount that I have to pay, the P, is greater than 0, but strictly less than $25, how much do I get charged for shipping? Well, I go back to the problem, and I see that the internet retailer charges $4.99 to ship an order that totals less than 25. And so the output value, if my order total is less than 25, is $4.99. The next piece of information that I'm given in the problem is that they charge $5.99 in shipping for an order up to $75. So if the price that I pay, the purchase total, if it's greater than or equal to 25 but less than $75, the amount of shipping that I have to pay is $5.99. Right, and so here are two different pieces, two different outputs for this function, depending on what the order amount is. And then lastly, in the problem, we're told that this company, this internet retailer, offers free shipping for an order over $75. And so here, we're going to say that it's $5.99 up to and including $75. And then the shipping cost is actually 0 if my order total is more than $75. So, what is the domain for this function? The domain is the collection of all possible inputs. The inputs here are the order totals. The cost that I have to pay for whatever items I'm purchasing. And so here, if I look at the possible values for P, right, I'm assuming that I'm purchasing something, so the price that I pay is greater than 0. And then I might end up actually ordering something really expensive. And so there's technically no upper bound on the order total for me. So my domain here is that I want to consider p-values that are strictly larger than 0 and finite, but I don't know if, right? It seems odd that I would pay like $1 million for something online, but maybe I could, okay? And so the domain here is the interval, right? In interval notation, we would do 0, infinity, and this represents all of those real numbers p that are strictly greater than 0 but finite. The other question from the statement of the problem is to write the range, or what is the range of g? We know that the range of a function is the collection of all possible outputs, and so what sort of outputs can I get? In other words, what sort of shipping costs can I get? Well, there are only 3 options. I can be charged $4.99 in shipping, $5.99 in shipping, or 0 in shipping. So my range just consists of those 3 possible values. And so the range in this particular example is just a set of 3 numbers. I'll write them in the order that they're written for the function, but that doesn't really matter. I could get $4.99 as a possible output, I could get $5.99 as a possible output, or I could get 0 as a possible output. To help us visualize this function, even though it's not required in the problem, we might sketch a graph of g. Graphing, I think, is something you probably did in the past. What would the graph of g look like? Typically, when we make the graph of a function, we put the independent variable, in this case p, on the horizontal axis, or the x-axis, although we don't have to put it there. And then we put the dependent variable, in other words g, or the shipping costs, on the vertical axis. Although again, that's not strictly required. So I have 2 axes, and now I'm only concerned with the p-values going from 0 to infinity perhaps. I'm going to just mark a couple of them. Here's p equals 0. Let's say this is p equals 25. The next value of interest for p is 75. Okay, my scale isn't a uniform scale here, but I'm marking these points of interest. And now I want to plot the graph. When I plot the graph, I sketch the outputs. I sketch the values. So if my p-values are from 0 to 25, not including 0 or 25, my output amount is $4.99. So there's $4.99. I'm going to put an open circle here at 0 because there's no output when p equals 0. P equals 0 is not in the domain of the function. And then I just have a horizontal line here, really, until I get to 25. Right? No matter what my p-value is between 0 and 25, my output is $4.99. For the next part of this piecewise function, from 25 including 25 to 75 including 75, my output is $5.99. Right? So here's the output, here's the height, $5.99. If p equals 25, that's how much I have to pay in shipping. If p equals 75, that's how much I have to pay in shipping. And then for any p value between 25 and 75, I still pay $5.99 in shipping. So again, I get this horizontal line. The last part of the graph has a height of 0, and that's what the height is when p is greater than 75. So for these p values out here, right, where p is greater than 75, my height should be 0. Notice that I'm putting an open circle at 75 down below, because this graph has to pass something called the vertical line test for a function. Right, this passes the vertical line test for a function. Okay, the statement of that test is in the book, but the idea is that from the definition of a function, every input can only have a unique output. And so for this input 75, it can't both go to 0 and 599. It can only have one of those values as the output. Another type of problem that you'll have to do in the exercises, and that is useful to do whenever you're given a function in a problem, or if you come up with a function that you want to understand, is to determine the domain. Okay, we just did that with the previous example, but here I'm going to determine the domain of a function if the function is represented algebraically with a formula. The two examples that I'm going to do here are show us two things that we want to watch out for, or that come up frequently when we're finding the domain. For the first function, let's say that the function has this equation g of x. Let me call it something else. We just used g a second ago. Let's call it f of x. Let's say f of x is equal to 1 over x squared minus x. Now, one of the things that you might remember from high school maybe, or maybe earlier than that, is that you can't divide by 0. And so here, in the formula for the function, I see that I have a fraction. Right? I'm dividing 1 by some number here. Right? I imagine plugging in some values for x. X is my independent variable. Right? If I were to plug in 2, right, what would f of 2 be? That would be 1 over 2 squared minus 2, and so that would be 1 over 4 minus 2, which is 1/2. Okay, that's how I compute a value for this function. And so when I'm finding domain, the real question is, what x's am I allowed to plug in? And so here, another way of thinking about that is, I need to figure out if there are any x values, so that when I plug them in, I get 0 in the denominator, because that would be bad, right? So, if I set the denominator equal to 0 here, I can figure out what x's make the denominator 0. How do you solve this equation for x? Well, this is a quadratic equation, but it's a fairly simple one. And one thing that I can do to try to solve it for x is to factor out an x, right? Each of my two terms have an x in common, and so I factor it out. When I factor it out, what am I left with? Factoring out essentially is dividing, so x squared divided by x is x, and then I'm going to have a minus, x divided by x is 1. Right, you can check if you distribute this x back into the parentheses, you get x squared minus x. Okay, this product now equals 0. When you have two factors multiplying together equal to 0, it has to be the case that one of them is 0. And so at this point, using logic, I can conclude that either x equals 0 or x minus 1 equals 0. And so this tells me the x's that I need to avoid, right? Because these x's would make the denominator 0. In other words, if x is 0 or if x is 1, the output value is not defined. And so the domain of the function f here, I'll write it in words this time. It's all real numbers except these two x values that I found that would make the denominator 0. So my domain is all real numbers except x equals 0 and x equals 1. We'll do one more example of finding the domain when we're given a formula for a function. The function this time is h of t equals the square root of 1 minus t. So here we'll consider capital H of t equals the square root of 1 minus t. And then what I'm looking for is the domain of this function, capital H. I mentioned in the previous example that when we're finding domain, one thing to watch out for is division, because we can't divide by 0. Another thing to watch out for is a square root, or really an even root. And what you might remember about roots is that you can't take a square root or a fourth root or a sixth root, etc., of a negative number. And so here, what I need is I need for this quantity underneath the square root, the 1 minus t, I need that to be greater than or equal to 0, because I can't take the square root of a negative. This is an inequality, but I can solve it for the independent variable t. And so in this problem, for the domain, I need 1 to be greater than or equal to t. Right? I just added t to both sides. A different way to write this is that the domain of capital H consists of all real numbers t that are less than or equal to 1. We can write that as an interval. That's the collection of values minus infinity, comma 1, and then I use the square bracket next to the 1 to indicate that I want to include 1 in the domain, because t could equal 1 here. For tomorrow, I'd like you to try the 1.1 problems that are listed in the syllabus, and we can begin class with any questions that you might have.